Hello. So in this lecture, we are going to start discussing about hashing, chapter 21. So we are going to discuss what is hashing and the hash code. We are going to explain it. And then we are going to discuss the techniques that will handle the collision, okay? And after that, we are going to go over a couple of examples, okay, for the implementation of a hash table, hash map, okay, and also Java collections hash map. Okay, so the first section is about the hashing concept. So what is hashing? Okay, and it is so the concept is uh, it involves a hash function, and later we will also say, okay, there are some the features for a function to be a hash function. So we use a hash function to compute a fixed size integer value. And this fixed size integer value, we call it a hash code. Okay. And then normally when we do hashing is we are going to hash on keys. Okay. And the key can be data of arbitrary size. Okay. So the idea basically is you have some data, okay, and then you apply some hash function, and then it generate some hash code. And there are some features later we will discuss, okay. And once we have this hash code, then we can use the hash code to find the index of the respective, like the key. Okay, so the respective some record. Okay, and so this fixed size array that's going to store um, the collection of items. Okay, and but the index is so the item where the item is going to be stored in the array is determined by the hash code. Okay, if we apply this concept, then that specific fixed size array, we call it a hash table. Okay, so this hash table, it will store the related information about the key. Okay, so this is a hash table concept. So what is the hashing? Okay, so the hashing concept is the process that we map the key to their corresponding values in the hash table using hashing code as indices. So this process, we call it hashing, okay? So here it involves the concept from, so basically here data is the key, apply the hash, generate a hash code. And then hash code is going to map the respective index of, we call it a hash table. Okay, so this process, we call it, the concept is called hashing. Okay, and because of this hashing, then we can it, store some related information regarding the key. Okay, so some relating the information, but based on K using key to find the index. So this will make the search more efficient. So efficient mapping. So basically, because of this hashing, so hashing enables efficient mapping of key value pair. Okay, so you have a key and then the respective values. We call it a key value pair. So one example is like the address book. Okay, so address book is that. So for address book, you have name, then you have the address. Is it so over here, name basically is the key part, and address is the value part. Okay, so then for each of the name and address, so this is a key value pair that, and if we apply hashing, then we can store it like in some array, okay, and this array it has some mapping, and that mapping will use the key to find the respective index. Okay, so then using this whole concept, it's a hashing, then it will make the whole mapping of the storing and searching much more efficient. Okay, so later we are going to see. Okay, so this is the general idea about hashing and its definition. Okay, let's take a look at this example. Okay, so it will help us to understand better about hashing, hash table, key value, okay, of this concept. So suppose like you have some major, we call it a major league baseball player, okay, information. So here it has name, and this may be some leaguer. This is the role, is it here? Or maybe the score or something. Okay, so each record has this kind of information: name, team, role, and the scores. Okay, yeah. So how do we store it so that we can do efficient mapping? Okay, so here the efficient mapping is means the key value pair. Okay, so key value pair. So in this scenario, maybe generally speaking, is it normally we can use name as the key. Is it? So value, then maybe the all of the remaining information can be included in value. Okay, you can define some structure to store all of the information. Okay, so this part then will be value, and this part will be maybe key. Okay, or if you have user ID, then you can use user ID as a key. Then this whole record will be the value. That's normally we used that. Okay, so then in this case, so like over here, we show is it, so we have this case of player names, okay, and then we can apply some hash function, okay, to generate some hash code. And later on, we will see in we can define the specific hash code, okay. And after that, we can apply it. Suppose you are going to store it in an array of size 1500. Suppose uh, this record contains 1500 records, is it? So if that's the case, then just think about it. Is it how do we map each player's information, is it, to this array? So what we can do is then after we apply the hash code and we do some bitwise operation, and then we do this module 1500. Okay, if we do module 1500, and then of the value will be between 0 to 1499, is it? So then the name can be, so basically, then in this case, it's name, then it's going to be mapped to a value between 0 to 1499. Is it? So because of this, then you can store the respective information. So in this case, we have the value, basically, it's this whole. So we can define a class. In this case, it's a player. That okay, and then you can store each player then in the respective array location. Okay, so array slot. Okay, so here, so we create this kind of map, the key value pair mapping. Okay, and because of this mapping, it's so here the mapping using the key player's name as key. So then just think about it. Once we have this, then if we try to find a one player, suppose like this Brian robots, suppose like the Brian as that robots. Okay, what we can do is you can just plug in this name to that hash. Okay, then it will generate a hash code, some integer number, is it? And then it does the bitwise AND operation with that 0x7 left something. Okay, and after that you module 1500. Then it will generate some integer. So the integer value basically in this case is going to be 819. Is it? So this 819 then will be this index of this array. Okay, so that you don't need to do one by one record search as it comparison to find player Brian robots. So you just apply this, then you can find the index, then you locate this player. So that's why we say after we have this uh, hash table created, okay, then it will be much more efficient to locate a specific record, just like what we did. Okay, so that's the whole idea about this hash table and its efficient and its benefits. Okay. So we can clearly see it can expedite the search. And we will also see that the search, the big O for this search, basically it's a constant. Is it? You don't need to do one by one comparison, not like the linear search is order of n. Okay, even binary search, then it's order of log 2n, but here it's order of a constant. Okay, it's just the time based on that hashing. So that's the example about how hashing actually is conducted. Okay, so in hashing, then we can see that a hash function is very important, is it? So not any function can be a hash function. So hash function, it needs to adhere certain principles. Okay. So first, it returns an integer value for an object. So so you plug in an object and it can return an integer value. Okay. And also it's one way. So the concept of this one way is it's computational easy to generate the hash code from the input. Okay, but it's not computational feasible to reverse the process. Okay, so we can have a hash object to hash code. But if you wanted to if you have a hash code, you wanted to get an object, so that's impossible. Okay, so we cannot, so the hash function must meet this one-way definition. Okay, so this is the first feature for a hash function must be one way. The second principal requirement is if two objects are defined as equal, then the hash code must also be identical. Okay, so this we call it deterministic. Okay, so same input will always produce the same hash output. Okay, so if the same object, then the hash code must be the same. And if two objects are not equal, then the hash code may or may not be the same. Okay, so here, not equal, but the hash may also be the same. Okay, so here, that's the third principle. It's collision resistance. Ideally, we shouldn't allow this to happen. Okay, but depends on the hash function. Okay, and so the hash function generally it's recommended the hash function should be computational difficult to find two different inputs that produce the exact same hash output. Okay, so that's ideally, but we cannot guarantee. Okay, so this is the requirement for hash function. And the insecurity hash is also used to try to guarantee like object integrity, as it. So you may also see this a lot, as it that SHA algorithm, okay, SHA, the SHA algorithm. So it's some complicated function. Okay, so this is about a hash function. And like previously, I explained for the hash table, the most advantage of hash table is it's a fast lookup. Okay, and it's order of a constant for a collection of objects. Okay, regarding store them in an array of size n. Okay, so the idea is so here is the hash code of that. You apply an object to a hash function, okay, and then after that we do some operation that can generate the index, okay. So over here it shows so you have some objects. So basically, generally speaking, we apply not to the we apply it to the key, okay, and then it also has a value. So it's from key to find the value. That's what we do the lookup, okay. So over here, it's only regarding the key, okay. So for key, then you apply hash function to generate a hash code like over here it shows. Okay. And then we can apply the module operation plus like previously showed is bitwise and some bitwise operations, and then you can generate the index. Okay. And because of this, yeah, that's why the lookup complexity is order of a constant, as it because it doesn't involve any comparison, as it is just directly apply the hash code hash function to key and then do the module operation, then you get the index. Okay, so that's about the benefit of its lookup. Okay, then how do we get the hash code? So in Java, uh, we can write a method called hash code. Okay, so in object class, Java also has a hash code method. Okay, so we can do override to provide our own implementation about this hash code. Okay, we cannot. So if you just use object, it may not applicable to all of the cases. Okay, so generally speaking, it's recommended to override the hash code method. Okay, whenever if you want to override the equal method. Okay, so because in this will ensure the consistency with the general contract of the hash code method. Because if you recall previously, we also said, okay, for the hash, it has a feature equal object must have equal hash code. So if you, for a class, if you override the equal method, then better also override the hash code method. In our previous discussion, when we override equal, we haven't override the hash code method. Okay, but from now on, we should also do this. Okay. And the hash code, it returns the hash code, some integer value with it. So here we give three scenarios. So if the object is an integer, then it return the integer value itself. Okay. If it's a character object, then you can return the character's Unicode value. Okay. If it is a string object, then we can use the following formula to calculate the hash code. Okay. So each letter, and then you do you times 31 to the power. Okay. Based on the letters the length of the letter as it and where it is in the string. Okay, so we can use this formula to calculate the hash code. Okay, and then for the hash code, if we have some user-defined class, that and it says if all the fields of a user-defined class have known hash code or the hash code method, then we can also, so in Java, this class, be careful, it's not objects class. It's a utility class function. It is a utility class, okay? So within it, it has the hash method, okay? And so for this utility class, it provides a group of static method, okay? That simplify. So the purpose simplify deployment without create an object. Okay? Different like the object for object, you need to create an instance of the object because here all the methods are static, so we don't need. Okay, and within this objects client has this hash method, so you can also go ahead to use. Okay, if it meets the condition. Okay, so like over here, that suppose class A has some three instances a variable x, y, z, okay, then what we can do for the hash code method, so you override it, is it? Yes, the simplest way we can do is you just call objects, then it's a hash method, then you just plug in. It's a three instance variable x, y, z. Okay, then it will calculate the hash code for us. Okay, like if you recall, previously we said it has kind of like a contract is it between equals and the hash code, is it? So if you override the hash code, then you also override. If we override the equal method, then you also override the hash code method, is it? And because of the hash code for the equals method, when we do the override, then we recommend we do like the following. Okay, first you determine if the object is object itself. Okay, and then you determine if the object is of the specific class as it you defined. Okay, and then we can also cast the object to this class. Okay. And then based on class A, so basically this is for class A. Class A, suppose it has three field X, Y, Z, etc. Then you need to compare each of the fields. Okay, so this while also, if you recall the previous slide, we just discussed the overriding of the hash code. Okay, so hash code just call the objects the hash method, is it, to directly hash X, Y, Z. Okay, so after we learn this hash code, then for our equal method in the future when we do the overriding. This is the recommended implementation for this equal method. Okay, and then yeah, if you recall previously, we also said like the hash function cannot guarantee is it a different object after hash. It will generate always generate different hash code. That's not a guaranteed. Okay, so if different object after we do the hashing generate same hash code. If generate has same hash code when you do the module operation, is it? Then it will generate then the same index. And the same index for two different objects. How do we store them in one location? Is it? So then there is a collision. So that's we needed to find some way to handle it. Is it? Yeah. So here, one way we can do is the array is not just the array about the object itself. Okay, so we can have an array of array list. Yeah. Okay. And you have an array of array list. So when conflict happens, like in this case, this player's information, oh, this is a book, this book's information and the 211, and these two, after they do the hashing and the module operation, they both have the index 0. So if we have array list to store them, then the first one will be the first element in the array list, and second one will go to the second one. So that can solve the collision problem. Okay, so this is one way we can use to solve collision. And there are some other approaches that we can also use to solve the collision problem. Okay. So over here, it's in the third section, it discuss the techniques to handle collision. Okay, so collision is because multiple key map to the same calculated index. Okay, and the two common approaches, one is called open addressing, the second one is called separate chaining. Okay, so in open addressing, it says the elements of the array directly store the key value pairs. Okay, not like the one that we previously, in the previous slide, explained. Okay, so the array directly store key value pair. Okay, then if collision occurs, the algorithm will search for the next available slot in the array. Okay, we are going to use some technique. We call it probing technique. Okay. The second one, so basically the one we just discussed in the previous slide, is called separate chaining. Okay, so elements of the array store linked data structure, like a linked list or array list, is it? And then the list will contain all the values that map to the same index. So this is how we handle collision. Okay, and regarding that open addressing, is it open addressing using probing? Okay, there are three different approaches that we discuss. So linear probing, quadratic probing, and double hashing. Okay, so linear probing is the most straightforward. Okay, so index I is directly calculated like what we already explained. Is it using hashing function and then using module? Is it? And if collision happens, then the algorithm will just check the next slot at like, suppose initially it's I, is it? And then just check I plus 1. If I plus 1 are also occupied, then you just check I plus 2. If I plus 2 occupied, you just move to I plus 3, okay, until an empty slot is found. Okay, then you store that value, okay. So in this approach, we can clearly see the offset from the original store is going to be 1, 2, 3 something, is it? So if the number of the items is equal to the array size, then all items will be stored in the array. So no problem, okay? But there is some issue with it here for the collision because excessive collisions can disrupt the original mapping, okay? Because when you take over I plus 2, I plus 3, maybe they are the original index for some other, um, for the true index, that so that will disrupt the original mapping, okay, created by the hash function, okay. So this will lead to the issue we call the exhaustive lookup, okay. So then it kind of destroy the benefits of the hashing, the lookup for the hash table. Is it? Yeah. Because then when you do the search after the hashing is not there, you need to do +1, +2, +3, kind of also go back to the linear search. Okay. And another, so there's another drawback of the linear probing is value tend to cluster together. Yeah. So then this will cause primary, we call it primary clustering. Okay. So this is about linear probing. Okay. The second is quadratic probing. Okay. So quadratic, so instead of just move I from I plus 1, I plus 2, okay, then you do I 2 to the 2, okay. So then it will be I plus 1, I plus 4, I plus 9, I plus 16. Okay, so quadratic, is it? Yeah, this does can reduce clustering, okay. But the downside of quadratic probing is not all values are guaranteed to find an available slot. Yeah, so there's some downside. There is another called double hashing. Okay, the double hashing, it will use a secondary hashing function. We call it f prime. Okay, for the key. In addition of the primary hash function f key, etc. Okay, and then for the primary index, we just use the after we do the hashing, is it? We do the module, is it? And for while the second hash function, then it defines, it use the constant, then minus the key, do the module. Okay. So then if a collision occurs, then the second hash function determines the step size for the probing. So then the index is calculated as what? I, then j times this secondary hashing. Okay. And then j takes on the value of 0, 1, 2, 3, 4, something. Okay. So then in this way, in this approach, is it then it can minimize the clustering and also provide a more uniform distribution of the values. So that's its advantage. So regarding all these three, it's about all of the values is going to be stored in the original array. Okay. For the other one, we call it chained. Okay, and then for the next section, it's about a simple hash table example. Okay, we will see that. And after that, we are going to take a look at the linear probing, okay, implementation for the hash map. Okay. And then we are also going to discuss the separate chaining, okay, for the implementation of a hash table. And then we are going to take a look at the example for Java collections hash table. Okay. Okay, so that's the major contents for this lecture. Okay, so here's some photos from national. This is not a national park. Okay, it's a national landmark. Okay, it's very beautiful. Okay, yeah. Yeah, this is another photo from that landmark. So where it is? So it's in Cooler Range. Okay, this is a national nature landmark. Okay, so that's all for this lecture. Next lecture we are going to discuss the implementation about the hash table. Okay, see you.